For an inductor, if we consider I to be our reference axis, then voltage leads by 90 degree, and for the capacitor, the voltage lags by 90 degree, but the resistance, current and voltage phasors are always in phase. LCR circuits are also used to change the impedance of the circuit and to increase or decrease the resistance of the current of different frequencies present in it. All these uses can be used individually or they can be used all together to get the wanted results in an electronic device. In the mathematical field, LCR circuits are not directly applied in the same way they are in physics or engineering. However, concepts related to LCR circuits such as differential equations and complex numbers have mathematical applications. Here are some connections. Differential equations. The behavior of LCR circuits can be described by differential equations. Understanding and solving these equations involve mathematical techniques, especially in dealing with the time-dependent behavior of signals in the circuit. Complex numbers. Analysis of LCR circuits often involves complex numbers. The impedance in AC circuits, including LCR circuits, is represented using complex numbers. This application ties into mathematical concepts related to imaginary and complex arithmetic. Frequency analysis. Mathematical tools such as Fourier analysis are used to understand the frequency response of LCR circuits. This involves mathematical transformations to analyze signals in the frequency domain. System dynamics. Mathematical modeling of LCR circuits can be approached using system of differential equations. This connects with broader mathematical concepts related to dynamical systems and control theory. While LCR series circuits themselves may not be directly applied in pure mathematics, the principles and mathematical techniques used to analyze and describe these circuits have applications in mathematical modeling, analysis, and engineering disciplines. LCR circuits. Electric circuit is composed of three passive elements, namely resistance, inductance, and capacitance, active element being the voltage source. Flow of electricity through LCR circuits. Electricity can be understood as a substance which flows through conductors such as wires. The rate of flow of electricity is called the current. Suppose Q is the electrical charge on a condenser of capacity C and I be the current, we have the following. I is equals to dq by dt or Q is equals to integral I dt. Potential drop across the resistance R is IR. Potential drop across the inductance L is L into di by dt and potential drop across the capacitance C is Q by C. Phasor diagram. The LCR circuit analysis can be understood better in terms of phasors. A phasor is a rotating quantity. The formation of differential equations for an electric circuit are based on Kirchhoff laws, and we discuss application based on the following linear differential equation of first order referred to as LR series circuit differential equation, which is L di by dt plus Ri is equals to E. This differential equation in the form di by dt plus r by L, I is equals to E by L, is a linear form of differential equation, that is dy by dx plus py is equal to q, where p is equals to p of x and q is equals to q of x, and the solution of the linear differential equation is given by ye integral p into dx is equals to integral qe into integral p into dx plus c. Differential equation for LCR circuits. The physical principle needed to derive the differential equation that models the LCR series circuit is stated as follows. Kirchhoff's law. The sum of the voltage drops across the circuit elements is equivalent to the voltage E of t impressed on the circuit. Steps to solve differential equation for LCR circuits. Solving the differential equation for an LCR circuit involves considering the combination of inductance, capacitance, and resistance. General steps to solve the differential equation for LCR circuit. First, we have to write the differential equation. That is, we have to express the Kirchhoff's voltage law for the circuit in terms of I of t and its derivatives. Then, rearrange the equation. Manipulate the equation to have the derivative terms on one side and other terms on the opposite side. Then solve the homogeneous part to find the homogeneous solution. Set the input voltage to 0 and solve the homogeneous part of the equation. This solution represents the natural response of the circuit. Then we have to form the homogeneous solution. Find the particular solution. Consider the particular solution non-zero. This represents the forced response due to the input. Then we have to combine homogeneous and particular solutions. The general solution is the sum of the homogeneous and particular solutions. Complete the solution and apply initial conditions. If initial conditions are given, use them to determine the constants in the general solution. Then simplify and evaluate constants. Simplify the general solution and evaluate any constants using the initial conditions. Thanks for watching. If you like the video, please subscribe to my channel.